Sets is one of the foundational tools we need to approach mathematics, and today we're going to look at a lot of different areas of sets, so let's get started. First, we're just going to define what a set is, and really a set is just a list of things. And so an important part of that is really the order doesn't matter. A lot of times we write sets, we name sets with a capital letter, like capital A, but we list the elements of the set with braces. So for example, if I have the set ABC, then that's just the set A, capital A, that have things in it A, B, and C, like a grocery list. And so just like a grocery list, it doesn't really matter what order we write things in, as long as we have the same elements, we have the same set. So when I talk about the cardinality of a set, I'm just talking about the number of elements in that set. So for example, for the set we have here, A, I use this bars like absolute value of A to denote the cardinality. Here we had three things. So we have a set with three things. We have a set with cardinality 3. What kind of cardinalities could you have? Well, obviously a finite number. So I could think of a set with k elements in it, for example. Maybe we'll just let B be the set A1, A2, all the way out to A sub k. And so there's a set with k things in it. What else could I have? How about a set with nothing in it? Yeah, we actually could. I could have a set that I open the list and close the list immediately. We call this the empty set. We denote it with the Greek letter phi. And this would be like going grocery shopping with just a blank piece of paper. You have nothing on your list. And that's totally fine. We can do that. It's like our set theory version of 0. Well, what about an infinite set? Could we have sets with infinite things? Yeah, of course. So we'd use this double stroke n to stand for the natural numbers. And that's the set starting at 1 and just counting up 3, 4, 5, 6, 7, etc. all the way up to infinity, out to infinity. These are the natural numbers. We could also go maybe in the negative directions, so we denote that with double stroke z. We call these the integers, and so a good way we list those out would be 0, how about plus or minus 1, 2, and so on, going out forever. So we call these the integers. We could also have maybe the set of fractions that we call the rational numbers. And so, I mean, what would this be? This would be like 0 and plus or minus 1, but also stuff like plus or minus 1/2 and 2/3 and how about 4/5. And I mean, there's all sorts of things we could think of to put in this set. We probably need a better way to list out this set. We'll do that in a little bit. But intuitively, I think we understand what we mean is all the integers and then the fractions that we commonly deal with. And then most of the mathematics you've probably had at this point dealt with this category, which we call the real numbers. And I mean, how do we even begin to list that? This thing has so many elements in it. So all of these have cardinality infinity, right? And it's okay to write equals infinity here, but the reals is like a different kind of infinity. So what we mean by this is we're going from negative infinity to positive infinity, and I write it that way because we are talking about this entire number line stretching from negative infinity to positive infinity. So there's a infinite number of things in the reals, but it's almost like a different category, and we could do a whole video on just that topic alone. Maybe we will one day. I want to go back to the rational numbers, and we wrote this out, but I'm not too happy with the way we wrote this out because I mean there's a lot of gaps, and I know sets are not ordered, so I could have written the natural numbers as like 1, 3, 2, 4, etc., and that would have been okay as long as they're in there in some way. But because of just our familiarity of numbers, we would like to kind of write the naturals in an ordered way, right? Well, what about the rationals? So we can't really capture it listing them out like that very well. So we want to introduce this idea called set builder notation, which is a great way to describe sets. Let me give you an example. Okay, so we're going to use the rationals as our example. Now, the rational numbers, I'm trying to think, what do the rational numbers look like? Well, we already mentioned they're fractions. So let's write that in general terms. How about like A over B? So the things in this set look like A over B. Now A over B can't be anything, right? We want A and B to be integers, and we want B to not be 0. Okay, I'm going to kind of unpackage what we wrote here for a second. And so in set builder notation, the way you want to read this is the elements in the set look like this. And if I write ELTS, that means elements, else. The elements look like this. and then they satisfy a certain property. This is the property that they satisfy. So in other words, our elements look like A over B, but they have to satisfy that A and B are integers and B is not equal to 0. And this symbol here means element of. And that's a very useful symbol to use. We use it all the time. Like say X is an element of A is an element of the integers, etc. Set builder notation looks clumsy at first, but if you get used to using it, it's very, very useful. In fact, why don't we do an example with set builder notation? All right, so here I have a couple of exercises. I want to list the elements in the following sets. And the first one says, hold on, I got to read what this means. And it takes a little bit of practice, but let's look. Okay, so it says, they look like this, the things in this set. So what does that mean? The things in this set look like X, where X is a real number. Okay, and then this part is a property that they satisfy. So the real numbers in this set satisfy X squared equals 9. Okay, so actually this one I could list out the elements here because there's only two real numbers that when you square them you get 9. That's -3 and 3. And so that set is actually just saying -3 or 3. You may have had an algebra class where they talk about the solution set. Here, the solution set to the equation x squared equals 9 is 3 and -3. We can say them in any order we want, and we can capture them in set builder notation like this. Now for that, set builder notation might be too powerful of a tool because we only have two things. But look at the next example. We have 6a plus 2b, where a and b are integers. And so we want to list out, we can't list out everything in this set, but maybe we can list out some things. And so again, the elements look like this, and they satisfy this property. So as long as we let a and b be integers, do 6 times a plus 2 times b, we have an element of the set. So for example, I don't know, why don't we let the b's be 0 for a little bit? So if b is 0, I could have 0 if a and b are 0. If a is 1 and b is 0, I get 6. If a is 2 and b is 0, I get 12 and 18. And of course I could do plus or minus if I want, so I got -6 in here. And a lot of other things like that. So these are just all examples where I let b be 0 and a be something else. I didn't list all of them out, of course. We could also let a be 0 and b have its turn, so maybe like 2, 4, 6 if b is 3, but I've already got 6 in there, so I'm not going to list it twice. There's no sense in doing that. So I have 8 and 10, 12, I don't want to list twice again, right? And so on. So here I'll let a be 0 that time. But I could also do things like, what about if a is -1 and b is 4? Okay, so if a is -1 and b is 4, what do I have? I have, let's see, 6 times -1 is -6. B being 4, that's plus 8. I get 2. I believe we get the idea of the elements in this set just based upon this definition. Again, set builder notation is very, very useful. You just got to get used to using it. All right, so let's practice writing some sets in set builder notation. For the first example, we have -2, -1, 0, 1, 2, 3. I'm trying to write this as set builder notation. I mean, what do these things look like? All right, so these things look like maybe n. And what's the defining property on these numbers? -2, -1, 0, 1, 2, 3. I think the next one would probably be 4, 5, 6, etc. These are just integers. So maybe I could just say this is n where n is an integer. Okay, now we shorthand this set as the integers, but the point of this exercise we're trying to just get used to converting sets into set builder notation. And I hope that makes sense. For the second one, again, I said this one's already in set builder notation. So what we're going to do is kind of like example 1, we're going to expand it out. So how should I read this? This is theta where tangent theta is undefined. Okay, so I'm trying to think. So if I graphed tangent, it looks kind of like that, and then it keeps repeating itself with these like lightning bolt looking things, and you have asymptotes here. And if I remember right, the asymptotes are like -pi/2, pi/2, 3pi/2, okay, and 5pi/2. And what's the pattern here? I have these asymptotes at like the odd multiple, an odd number times pi/2. Okay, so I think I mean, if I was going to list this out, I'd say -pi/2, that makes tangent undefined, pi over 2 is tangent undefined, 3 pi over 2, 5 pi over 2, 7 pi over 2, etc. We could rewrite this in set builder notation. I think it'd be a little bit clearer for us. What we mean here is we want these guys to look like, I know. We want some sort of odd number times pi over 2. So let me write odd times pi over 2, where that odd number, is an integer. I just got to figure out a good way to write odd. So you may have seen this before, but we can write an odd integer as 2k plus 1, where k is some integer, right? So every odd number is 2k plus 1. Okay, so let's try that then. Let me erase the odd word, and we're going to write the places where tangent is undefined as 2k plus 1 times pi over 2, where k is an integer. And this time I wrote a straight bar, really depending on your instructor or your textbook. Sometimes we write straight bars, sometimes we write colons. I've been trying to get in the habit of writing colons just because I think sometimes it's a little clearer. But straight bar is very common as well. If you see that, that's what we mean by that. There's one other concept I think is very important for the basics of sets, and that's the understanding of subsets. If I draw a set out like this, A, and this is just a collection of stuff, right? So I have A1, here's A2, A3, and remember, sets don't have to just be numbers, they're just elements. So maybe I have like orange and doggy, right? And something else, I don't know. How about like, maybe we also put in like the set that's got like a smiley face in it or something like that. Okay, so this is a set, and what I want to do this time is just take a few of those things. I don't want all of them. So maybe I like A1 and I like doggy. I want those in there, and I want orange in my set. Well, if I just take that as a set itself, well, I've already said it. It's not a dog, it's a set as also. So we can label this set B, and B exists in this set. And so when we say a subset, that's exactly what we mean. The way we write it is B is, almost looks like a less than or equal to, but it's like a C shape, less than or equal to A. And this means B is a subset of A, which means everything in B is in A. Maybe a better way to say that is, if X is in B, then X is in A. That's what we mean by a subset. It doesn't mean the opposite, though. It doesn't mean that if X is in A, then X has to be in B. So a good example of this is I live in Jackson, Mississippi. So if I'm in Jackson, Mississippi, then I'm also in the United States of America, because Jackson is a subset of the USA. So I think that's a good way to visualize what we mean by subsets. On a broader context, let me think. How about every type of turtle is a reptile? So the set of all subspecies or species of turtles, that set is a subset of the set of all reptiles, which is a subset of the set of all animals. Okay, so we can have these nestling subsets. Alright guys, this is the beginning of set theory. I hope it makes sense. I'm telling you, it's worth practicing these because we use sets in so many different contexts. It can be confusing at first, but it's really not a hard concept, and I think sometimes we just make it too hard. If you have questions on this, please let me know. I'd be happy to help. I'd be happy to kind of sort out some stuff. Leave it in the comments, send me an email, whatever you need to. Just keep practicing it. You're going to get better. You just got to learn to read this language. Alright guys, I'll see you later. Thanks for watching.